In our last lesson, we talked about the basics of light and how it interacts with bonding electrons in the UV invisible light region. Today, we are going to focus on how infrared light can cause molecules to vibrate at different frequencies. The vibrations caused by IR are actually stretching and bending in individual bonds. Each bond type will have a different strength, and it will interact with IR light at specific frequencies. Only certain types of vibrations can interact with the IR signal, the asymmetric ones that change the dipole. Symmetric stretches don't interact directly with the IR light, and so we will only see certain interactions. Typically, these spectra are plotted as percent transmittance against wave numbers, which are actually a frequency unit with a value of inverse centimeters. Wave numbers can be obtained by simple unit conversions, either by taking 1 over the wavelength in centimeters, or by taking the frequency over 100 times the speed of light. Remember, since this is a frequency measurement, the higher numbers are higher in energy. In addition to the information given by wave numbers, we also pay attention to the strength of absorption bands. Vibrations with a significant change to the dipole often interact strongly. For example, the C double bond O carbonyl stretch always gives a strong absorption band. Because functional groups contain the same number of bonds, they have very similar IR spectra in certain regions. For example, the carbonyl stretch generally shows up in a very similar location no matter which molecule it is part of. These characteristic absorption strengths and locations are found in tables that ideally describe both factors. My assumption is generally that if you have access to an IR spectrum, you'll also have access to a shift table, and so I ask that you practice using one rather than memorize the shifts. The exception to that is that I want you to memorize the regions of an IR spectrum based on the types of stretches that occur in each region. The lowest energy region on the right is the fingerprint region. There are a lot of single bond stretches here, like C-C stretches and CO stretches. This region is full of useful but difficult to interpret information. In many cases, it is best used comparing against reference spectrum, hence fingerprint region. The next lowest energy is the double bond region, like alkenes or carbonyls. Because carbonyl stretch changes the dipole much more than alkenes, carbonyls tend to have very thin, strong bands in this region. The carbonyl stretch will change locations based on the functional group in conjugation, and can give enormous amounts of information. Triple bonds, like alkynes and nitriles, show up in the next region. The highest energy peaks come from carbon-hydrogen, nitrogen-hydrogen, and oxygen-hydrogen stretches. There are usually so many carbon-hydrogen stretches that this peak is more useful in its absence rather than its presence. NH and OH stretches can be really helpful indicators, of course, but OH stretches can sometimes come from a wet sample, one that has water in it, rather than an alcohol or carboxylic acid. Why do these show up in the order that they do? We can think about the bonds like a spring. Decreasing mass on a spring makes it harder to vibrate the spring. This is easiest to understand if you think of the spring having some stiffness. For this reason, our highest energy comes from heavy atoms, hydrogen single bonds. Stiffer springs also increase the amount of energy needed to vibrate, of course, which translates to heavy atom single bonds appearing at relatively low frequency, but the stiffer double bonds appearing higher, and the stiffer still triple bonds appearing higher still. Of all the heavy atom hydrogen stretches, C appears at the lowest energy. sp3 carbon hydrogens are held the farthest apart and have the lowest energy stretches. sp2 carbon hydrogen bonds are shorter and have stretches that are higher energy. And sp hybridized carbon hydrogen bonds are higher energy still, as the sp orbitals are functionally more electronegative. Nitrogen-hydrogen stretches are higher but also broader, and OH stretches are both very high energy and also very broad. We know that some types of bonds have stronger intensities than others. because they change the dipole more than others. This also comes into play when alkenes are placed differently in a molecule. A terminal alkene can change the dipole much more significantly than an internal alkene. The alkene stretch can all but disappear in symmetrical or nearly symmetrical molecules. The OH stretch is really strong and really broad. They're typically around 3,300 or so. When an OH is part of a carboxylic acid, though, the stretch is lower energy, but still broad. It will overlap the CH stretch, but can be easily distinguished because of how broad it is. Really, any hydrogen bonding hydrogen is broad because the hydrogens are constantly swapping partners. OH stretches are the broadest that we normally see, but NH stretches will also be broad. The carbonyl stretch is one of the most clear peaks because it is strong and narrow. It is also one of the most useful. Even though these frequencies appear in a wide range, they can give a lot of information because different carbonyl containing functional groups still show up in a very thin window. But conjugation can make things appear a little bit differently. So in this example, we see that the ketone peak actually moves down in frequency as we add conjugation. Triple bonds aren't particularly common, but they are usually easy to differentiate because no other bonds appear in this region. Both alkynes and nitriles appear in the same range, but alkynes are always weak, and you can see the sp carbon-hydrogen stretch if it's terminal. Because of the difference in electronegativity, nitriles give much stronger absorptions. Alkene bands can be difficult to work with since they show up in the same region as carbonyls, but are thinner and less intense, and so can be hidden. Aromatic peaks show up much lower because they are not alkenes. Alkenes and aromatics that aren't apparent can still be identified by bending in the fingerprint region. Here is a detailed list of these modes. Again, the value here isn't in memorization, but in application. CH stretches are both weak and also common, so they show up very strong in many spectra from sheer quantity. When they don't show up strongly, it's a big deal. For example, the very weak CH stretch just above 3000 indicates that there are not many CH stretches in the benzophenone molecule shown. NH stretches tend to be stronger and narrower than OH stretches. Amines and amides can be primary, secondary, or tertiary, which means that they can have 2, 1, or 0 hydrogens. In the spectrum shown on top, the two leftmost peaks are the NH stretches. In the middle spectrum, the leftmost peak is NH. The bottom spectrum doesn't show any NH stretch because there's no hydrogen on the nitrogen. Often IR can be used to determine structure, or at least indicate a few possible structures. Many times the formula is given, and units of unsaturation will hint at structural possibilities. For 7 carbons, we'd expect 16 hydrogens, but since there are only 8, we know that there are 4 units of unsaturation in this molecule. I usually like to start looking for O stretches if a molecule has an O, since OH stretches are strong and clear, and carbonyl stretches are as well. Ethers have stretches that show up in the fingerprint region, but you can also tell by not having other indicative stretches. This molecule has a clear OH stretch around 3300 and no carbonyl stretch around 1700, so we know that it's an alcohol. So if the unsaturation doesn't come from a carbonyl, we need to figure out where it came from. The fact that our CH stretch is particularly weak suggests that we might have a benzene. Benzene has 3 double bonds in a ring for a total of 4 units of unsaturation, or index of hydrogen deficiency. That checks out as a possibility, especially since we don't see any triple bonds. We can also check for substitution peaks. There's a strong peak around 800. This is probably indicating para-substitution, which tells us that there are 2 groups coming off the benzene. With a formula of C7H8O, we know that we'll need a methyl for the extra carbon, and it will be para to the alcohol. This is an example from 15.6a. You should also do unknown 2 and 3 that are in sections 15.6b and 15.6c.